Hi! In today's video, let's take a look to see if we can do some non-destructive analysis on some of these cheap fuses to determine the maximum rated current with reasonable accuracy. And the type of fuses we will be talking about today are these standard fuses, not those polymetric PDC fuses or PPTC fuses. Of course, there are a lot of parameters in the specifications of a fuse, such as the speed at which it blows, the I squared T value, sometimes also called the melting integral, which is proportional to the amount of energy the fuse would let through before it interrupts the circuit. In some higher energy applications, we need to worry about the breaking capacity, which is the maximum current that can be safely interrupted by the fuse, comes into play. And we also have rated maximum operating voltage, typical voltage drop, temperature derating, so on and so forth. Here, though, we are only going to be concentrated on one parameter, and that is the maximum rated current. And in a lot of applications, especially in common consumer electronics, this is the main parameter that matters the most. So back to the title of this video, why it is desirable for us to do non-destructive testing. After all, we can easily just ramp up the current till the fuse blows and measure the current rating that way, right? Well, yes, of course you can do it that way. In fact, if you purchase your fuse from a reputable manufacturer, such as Littelfuse, Bussmann, Mersen, you can just rely on the specs given, as fuses from these top-notch manufacturers have been thoroughly quality controlled. But you can also buy these no-name brand fuses from Amazon. Although they are rated for specific interrupt current, there's no guarantee that the specifications are accurate. And even worse, there's no guarantee of the uniformity of the fuses that have the same current rating. So even if you test out one of the fuses that, say, is in spec, there's no guarantee that the next fuse you pick from the same batch would not have a drastically different interrupt current rating. So how do we actually do the non-destructive test? Well, we can simply measure the IV curve across the fuse. You see, a fuse is typically made of an alloy from, say, tin and lead, or some other materials, which typically have positive temperature coefficient. So let's do a little bit of math to see how we can do the estimate. Let's say we're trying to measure the resistance of a piece of wire, and the tempo of the wire is alpha. We can write down the relationship of the resistance at temperature T as a function of the tempo as RT equals RT0 times 1 plus alpha times delta T. And here the RT0 is the resistance of the piece of wire at temperature T0. T0 is typically at 20 degrees Celsius. And alpha here is our temperature coefficient. Delta T is basically the difference between the current temperature and that of T0. So for temperature, the delta T, for temperature greater than T0, delta T really just, we can write it as T. And now we can rearrange the terms to make it easier to read. So we can move the RT0 to the left. So we have a ratio of RT over RT0. And on the right-hand side, we have 1 plus alpha. If the temperature is far greater than T0, we simply can write it to delta T as alpha T. And for materials commonly used in fuses, and in fact, for the majority of the metals, the alpha is in the range of 0.004 to 0.005. So let's assume alpha equals, let's just say 0.004. And again, we can write this as RT over RT0 equals 1 plus T over, in this case, is 0.004 is 250. And the reason I wrote it this way is you'll see that it becomes a lot easier for us to explain what is going on and what we should expect when we are measuring the resistance ratio here. So when the temperature is at room temperature, this term is roughly 0, then we will have RT over RT0 equal to 0, which makes perfect sense. Now, for any temperature above that, as the temperature increases, we see that this ratio becomes greater than 1. When the temperature reaches, say, 250 degrees in this case, then we will have RT over RT0 equals 2. Basically, the current resistance would be twice that the resistance at room temperature. And if we increase the temperature even further, say at 500 degrees, then we will have a resistance twice that the resistance at room temperature. Although we don't know at what temperature the fuse would be melted, we do know that fuse materials melt at a significantly lower temperature than, say, copper material. And copper melts at about 1000 degrees. So let's say the fuse we use could melt anywhere between 250 to, say, 750 degrees. So what this equation is really telling us is basically when the measured resistance is 2, 3, 4 times larger than the original resistance, that's when the fuse is about to blow. And that is still quite a bit of a variation. And as we can still range temperature between 250 to 750, and this ratio can be anywhere between 2 to 4. And but in reality, though, it actually doesn't matter that much. And as we can see here, if we plot the current versus our RT over RT0, you will see that the curve is exponential here. So towards the end, we have, for example, here is where at the current, let's call it IC, critical current, we have a ratio of 2, and 2, 3, 4, as you can see here, they are, the current here is really close. So you may have about 10% variation, 20% variation, but as far as the fuse is concerned, we can reasonably assume that as soon as it reaches 2, let's say the critical current here, any current rate increase beyond that would cause the fuse to fail. So this is what we're going to be relying on to test our fuses non-destructively. Okay, enough talking. Let's do some measurements. And here is a setup. I have a power supply in the background that is hooked up in series with this electronic load. And the fuse to be tested will be placed between this pair of alligator clips. And right now I'm monitoring the voltage across these alligator clips using this set of leads on this multimeter here. So you can see it's 16 volts because the circuit is open currently. And but once the fuse is placed inside here, that would be monitoring the voltage drop across the fuse. So that's the plan. And for the fuse, I'm going to start with a 1 amp because that's just a pretty common fuse. So I'm going to just pick one out and place that between the alligator clips. And I like this kind of alligator clips because they're really, they have really sharp jaws and they can clamp on anything pretty much very, very securely. So that's what we need here. So now you can see that we have a 0 voltage drop. That's because we have turned off our electronic load. So now let me turn on the electronic load. And what we're going to do is we're going to step through the current, maybe 100 milliamps at a time, so that we have enough data points. So let's start with 100 milliamps. And here we're recording the voltage drop. Now, I could probably turn it into millivolt range to have a better reading. But in reality, it doesn't really matter as we increase the current here, we're going to see this ramping up. So we just want to record some approximate value here. And what I'm going to do also is to have it settle for a bit. And now, when the current is low, you don't need the settle time that long because the fuse is not heating up yet. But as you will see, when the current started to grow, started to increase further up, you will need to have a longer settle period so that we can let the voltage settle down. So anyway, so let me place this in sight here, and we will start ramping up the voltage and the current, and we will record at each step what the reading is. So our first data point is, here's our V and here's our I, and we have 0.015 and we're at 0.1 amps. Now I'm going to increase it to 200. And you can see we have 0.03 and we have a current of 0.2 amps. And it's fairly linear at this point, which is to be expected as we are pretty much just measuring the resistance of that fuse. And right now it's settled at 0.262 volts, and I suspect it's still going to go up if I wait long enough. But for now, let's write it down as 0.262, and let's keep increase the current through. As you will know that for all fuses, you can overcurrent it quite a bit, and for most of the fuses, it's roughly between 20 to 100% before it will blow. The one thing you will notice is that as we started ramping up the current beyond the rated current, the voltage would continue to rise faster and faster. So if you look at this chart here, if you remember what we talked about earlier, when we have the resistance doubled, that's the point where we think it has heated up substantially. So now at 0.1, you can see that at 0.1 amps, the resistance is roughly 15 milliohms. Is that what, 15 million? Oh no, it's 150 milliohms, 0.15 ohms. But at 1 amp, we started to approach 0.26 ohms. So we're actually getting pretty close to that factor of 2. And now you can see we're at 1.1 amps, and now we're recording 0.368, 369 volts, and I suspect it will probably go up to 70 if I wait long enough. But let's keep ramping it up. And in the meantime, what I'm going to do is I'm going to later on put these numbers in the spreadsheet, and we can show you what we're seeing on the on this relationship of the R over RT, RT over RT0, and versus the current. And we'll have a nice plot to show you the relationship. So now let's increase it to 1.2 amps. And now you can see that the voltage increases dramatically. So I suspect right now we're already at over the factor of 2. But remember, the fuse, because of the material it is made of, we don't know at which point it will blow. But there's a factor between 2 and 5 and 4. So really this voltage can keep increasing quite a bit before it finally blows. But right now we're at a point where we can reasonably assume we're approaching the final current limit. So right now we're at 1.2 amps, and at some point I suspect we will be able to see the fuse started glowing because it gets so hot. Now in normal usage you will never want to get this close to the maximum current because of the temperature derating and a lot of other factors built in. So really, as far as the normal usage is concerned, we're already beyond the designated maximum current. But just for fun, let's start ramping it up even more to see what we got here. So right now you can see that the voltage still keeps rising because it has not settled yet. And if you remember that we started with 0.59, so right now it's already 0.606, 07. It still has not settled. But let's call it 0.607. And let's increase it even more. So I wanted to, let's see if we can hit 1.3, and I think we should be able to. And I'm not sure if you can see, but now the fuse is actually started glowing. So let me zoom in, and you can see here. You can see the fuse is glowing red. So which means we're really approaching, and now I need to turn it down a little bit because otherwise it will blow. But right now we're at 1.2, 1.8, and it's increasing very fast. So right now, what I'm going to do is I'm going to turn it down. I'm going to write down the the voltage reading, and so that we have a reference when we plot it out. So right now, this is, I actually turned it down a little bit because I don't want the fuse to blow. We're doing non-destructive tests, remember? It went to 1.29 volts at 1.3 amps. So now we can ramp down the current to 0, and we will plot out the data points and see what our results are. So that was the properties of that 1 amp fuse. Now I think what we're going to test one more is a 0.1 amp fuse, and to see how it stands up. I would expect that the property of the 0.1 amp fuse and the 1 amp fuse to be quite similar. In fact, I would expect all these glass fuses to be pretty much similar. But let's take another look of this 0.1 amp fuse. Not sure if you can see it, but indeed it is spec'd at 0.1 amp. So let me set it up, and we will ramp up the current and see how it holds up. Now to do that, I'm going to turn on the meter again. This time I'm going to start at 10 milliamps increment, just because this is a 0.1 amp fuse. So first I'm going to start at 10 milliamp. Now the voltage drop here is quite low, so I'm going to change it to milliamp range. Millivolt range. So we can kind of see what is the voltage drop. Now, when the current is low, the voltage drop might not be that accurate, as we do have some contact resistance here. So I might do a couple of runs before I finalize the numbers. But at 0.01 amp, you can see the voltage drop is 3.7 millivolts. And let's ramp it up to 0.02. It's 7.2. And 0.03, it's still pretty linear. 10.5, 0.4, 14, okay, 0.05, 17.5, 17.6, it's still very linear. 0.06, 20.8. So far, we have seen that the numbers are relatively linear till this point. Yeah, so 0.07 amp, so this is 70 milliamps at 70% of the rated capacity, and it's at 24.4 millivolts. So that is still very linear. Later, I'm going to provide a graph for the numbers we're measuring here, so you will see exactly what we're talking about. At the 0.08, it is still very linear at 28 millivolts. So let's just increase it. 0.09. So at this point, I think this fuse might actually be over 100 milliamp. The reason is that when we saw that earlier, when we were testing the 1 amp fuse, as it approaches its maximum rated capacity, we can see that the current, as the current rises, the voltage rises more than the than the interval that was at lower current, because the resistance of the fuse had increased dramatically. So we did not see this here because I suspect it's still not heated up. So let me keep doing this, and I will report back at what point I think the fuse is going to blow. So this is unbelievable. Right now we're 6 times the rated current, and we are still pretty low in our ratio in terms of the resistance change. So I suspect we can still go up further. So now let's ramp it up to 700 milliamps. So we can see that at 900 milliamps, we are actually approaching that 200% in terms of the resistance value. So that means that this is approaching the point where the fuse is about to blow if we increase the current any further. But that tells you how far off this rated current is for this 0.1 amp fuse. And before we wrap up the video, I thought I would just do one more test. This time, instead of testing one of the standard fuses like we did with the 0.1 amp and 1 amp fuses, we're going to test an HRC fuse. And so like this one. So this is an HRC fuse, and typically these kind of fuses are very expensive. So you don't really want to just test for the sake of testing by blowing it up. And what we're going to do is we're going to do the non-destructive testing as we did before. But this one is rated for 630 milliamps. So we're going to put it in and see how it behaves. Now, because these kind of fuses are sand-filled and they have a relatively large thermal mass, so it's going to take a long time for the current to settle. when we adjust our current intervals. So what I'm going to do is I'm going to set it up, and we'll ramp up the current gradually, but I'm going to do that off the camera so that you don't have to wait, and we will see what we get. So let's set it up, and now I'm going to start it as, let's put it on our millivolt reading, and we're going to put 100 milliamp through. So now we're at 199 millivolts, and I suspect that the voltage actually going to drop a little bit because we're holding the fuse, and that was a little bit warm. So I'm going to let it settle, and then we're going to increase the current through the fuses, through this fuse, and we'll see what the voltage measurement is. And at the end, I'm going to show you the chart, and we will go from there. So now we have ramped up the current to 750 milliamps, and that is about 120 milliamps above the rated 630 milliamps rating. And the voltage drop across the fuse right now is at 2.115 roughly volts. And so that translates into a resistance increase about roughly 60%. And I will later on verify that with the data that I logged so far. But it does take quite some time for at each current interval for the fuse to sufficiently heat up. So now what I'm going to do is I'm going to further increase it, and it looks like we're stabilized at around 2.394 volts, and so that roughly translates to about a 67% increase in the resistance. So we still have some room to go. So now I'm going to attempt to set this to 850 milliamps. And it's a couple of minutes later, as you can see, that the voltage is still rising. And at this point, we're already at 90% higher, the resistance currently being measured. So there's no doubt that we're very, very close to the point where the fuse is going to blow. And I think if we just stay at this current for long enough, we will exceed that 100% resistance increase. So that is at a point where, you know, it will be the fuse would blow at any moment. So I think I'm going to stop the experiment right here, because I think you got the idea. This will definitely approach 3 volts, and at which point we will be over that 100%. So because I don't want the fuse to blow, and I'm going to turn down the current right now. In fact, I'm just going to turn this active load off. So I hope you enjoyed the video and learned something new. Videos like this takes time and resources to make, and if you like the video, please remember to share and subscribe. According to my channel's statistics, only less than 10% of the viewers have subscribed to my channel, and my goal is to achieve at least double that number and increase my viewer base over time. So your subscription goes a long way and is greatly appreciated. As always, thanks for watching the video, and I will catch up with you next time.